Welcome back, Science 8. As you can hear from my voice, I'm using a microphone. I am recovering, but still my voice is a bit horsey. Today we're going to conclude our chapter 2.2, or you can say workbook number 4 of Unit A, which is about concentration and solubility. Compared to the last goal, our goal today is pretty similar. Last time we talked about how depends on the amount of solute, the concentration of a solution is different. Depends on the amount of solute, solvent should be the same size by the way. If you have less solute, we call it diluted solution. If it has more solute, we call it concentrated solution. Okay, let's get this thing rolling. So concentrated solution have a relatively a large amount, as you can see from the laser over here, a large amount of solute compared to a small amount of solvent. But that does not necessarily mean the solvent is always small. It can be whatever intermediate size too. So I want you to look at the picture over there. If I count the number of water, let's use blue color for the water. We have 1, 2, 3, 4, 5, 6, 7, 8. We have 8 molecules of H2O. On the other hand, imagine the solute. Some people may wonder why it has two different color. It's because a lot of solutes are a combination of it. We call it compound. It's not pure matter. Sometimes it can be, but pure matter does not dissolve well. They react. So let's say table salt, NaCl, something like that, sodium chloride. If I count both of them together, you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We have 14 molecules. If I go one by one as a pair, that's at around 7 sodium chloride molecules. You may notice that, oh, Mr. Kim, there's 8 water and 7. So shouldn't 8 be bigger? If you look at that as a holistic way, yes. But if I look at separately, sodium by itself and chloride by itself, we will have way more number. So this is what the chemistry or chemist, if you will, or any scientist needs to be careful. Just because the mass number is smaller, that does not mean we have actually less molecule. They separate each other in water. We call it dissolving. And by having that, we can have more numbers. Let's look at diluted solution. Diluted solution is way more straightforward. We just have more solvent. And I like to say relatively more solvent compared to the concentrated one. And that's obvious when you look at the diagram on the right side. I'm not going to even bother counting. If I say in terms of analogy of if you shine the light upon, like for instance, if I have a flashlight that go from left to right, you should have most of them coming out, not filtered a lot. Quite transparent. That's a fancy way of saying it is clear. Now let's think about concentration. Now, some people may know at this point, some people may not know, but concentration at this point, you should get the idea it's about the quantity. AKA, we need number to represent How things are concentrated. A lot of people use percentage as an example. Concentration, ladies and gentlemen, because it's about the quantity, it should be measurable using different method. However, whatever the method that you use to try to communicate, it should in the end represent the exact amount. There are some margin of error, but you should not estimate the concentration. In actual chemistry reaction business. The reason being is even 1% differences can cause dramatical change. Remember, these molecules are really, really tiny to see. So even, let's say, you estimated, oh, 1 more milliliter of solute. It doesn't look like a big thing, but in the end, 1 milliliter can have thousands and millions of molecules additionally. So just for the heads up. This is the reason why, for example, if it's vinegar, if it's normal vinegar, it's about 5% concentration. If it's a little bit more concentrated, like pickling vinegar, it should still set a little higher, but not much. Just 2% difference, but it's still strong enough. All right, let's do one classroom example. I personally changed this question just a little bit, as you may notice at the back, but I'll let you decide. The question asks, what is the concentration of 50 grams of sugar? 50 grams of sugar in 100 ml of total solution as water was solvent. And we need to calculate the concentration. There are, in the end, so many different ways, but I'm going to go through symbolic 3 different ways that a lot of people use. Before we getting into, there are 2 things that I need to tell you. For water, if you don't know about this, that's okay. You didn't learn about this in previous sciences. Now you need to know. For water, 1 milliliter of water is equal to 1 gram. So I can change our milliliter into gram situation. Also, that's one thing. It only works for water. Water density is convertible to volume to gram. Now, also another thing. Concentration, in the end, it's about fraction ratio. How many of a portion over total? Concentration communicating fraction or decimal, or sometimes percentage after. So here's what you do. The very first way, we're going to do calculation of gram per milliliter. That's a one way of showing concentration. The next one, gram to gram. The next one, we're going to go percentage. It looks tough, but in the end, you'll find, oh, it's a piece of cake. So here's the thing. I don't want to say like a formula, but if you like to think about formula, feel free. You guys know that fraction, when it comes to any type of fractions, the total goes to the bottom. That's a fancy way of saying solution amount goes to the bottom. On the top, what do you think it will go? Something that being dissolved. In this case, solute. So if you like to memorize this as a formula, feel free. It's a solute over total. In this case, it's a sugar amount over solution. Then it's super easy. It's 50 gram over 100 milliliter. Can I simplify this fraction, 50 over 100? Yes, you can. I can divide it by 10 and make it into 5 over 10. Can I still simplify? Yes, we can. I can divide both top and the bottom by 5. 5 divided by 5 is 1. 10 divided by 5 is 2. So the thing is this is 1 gram per 2 milliliter. That is your concentration in number. Or also, you can I write in fraction? 0.5 gram per milliliter? Feel free. That's a one method. We represent gram, which is a mass of solute over solution's volume. We can also do weight by weight or mass by mass comparison. Same thing. Sugar gone, same situation. Solute on the top, 50 gram. Now, do you guys remember that when it comes to water as a solvent, I can change milliliter to gram. So instead of 100 mil, you can put 100 gram. But who care about the format of the unit? It's in the end 50 divided by 100. So long story short, it's 1 gram over 2 gram. Or you can say this is 0.5 gram per gram concentration. Identical if, like I said, water was used as a solvent. Percentage is even easier. So it's a two-step part. Same thing over here. You guys need to remember grade 7 math. In order to get decimal to percentage, what number, magic number do I need to multiply? You gotta multiply by 100. So once you get to that ratio 0.5, just multiply by 100, then you will get 50% concentrated. And that actually should make sense because look, 50 is half of your whole content. So that means out of the whole 100 ml solution, half of them are sugar. So we did a quick example of how to communicate. I'm gonna go with each of them a little in detail. The first method, as you can copy, we compare volume by volume. That means volume of solute over volume of solution. Then multiply by 100%. That gives you percentage volume of volume. Most of the time, people use the same unit, milliliter over milliliter. Second part, which is what I did before, the very first one, we can compare mass to volume. Mass to volume, like in that case, you will have mass of the solute over volume of solution. We do not make it into percentage, just this ratio remain. However, people try to use a certain volume like 100 mil. We didn't do this conversion, but if I do real quick on the side, you guys remember that it was 1 gram over 2 milliliters, something like that? You just need to somehow multiply by a certain number to get 2 to 100. I want you to think about the number. 2 times blank make 100. What goes into the blank? 2 times 50. Then you will get the idea. 50 gram per 100 mil is a concentration if you like to go with the mass over volume. Some people still put percentage method in addition to that. I didn't see a lot of that case other than commercial use like vinegar. But if that's the case, then from here you multiply by 100. So 50% concentrated, something like that. It exists, but a lot of times I found if it's mass volume ratio, people use it the most. Percentage mass by mass, same thing. Mass of the solute over mass of solution. Then multiply by 100. Note the fact that they use same unit, gram, gram, milliliter, milliliter. So you guys probably get the pattern. This is what you will learn in grade 9. So I like to say only a few things. Some people may hear ppm, parts per million. It's for very, very low concentration in a very, very high amount of total solution. So have that in your mind. So the way that you mathematically display your understanding about the concentration, you may know at this point that it's actually comparing how much solute do I have in total solution. Now, in addition to that, imagine you have two different beaker with unknown concentration. In that case, you need to know, first of all, it is very, very important for you to know exact quantity of solute. What I mean by that is how much of chemical did actually go in to make that solution. We need to know that exact quantity. Most of the time for junior high and high school, we use gram, how much mass that is involved. Also at the same time, we need to know how much volume. This is more like a control variable, same volume, because if the solvent amount change, the mass increase, the total solution's mass. So we need to know that exact quantity of solute and don't assume, and then also in a condition that same volume of solvent was used. So let's do a quick example. A quick example. Now we have 10 grams of salt in 50 ml of water, and know the fact that salt really doesn't change the volume, so you can assume in this case 50 ml is a number of solution, volume of solution. You can think it in that way. The next one is 25 grams of salt in 100 ml. Which one is more concentrated, which one is less concentrated? We can find it out. So let's do a calculation. What I'm going to do is I'm going to do gram per mil concentration comparison. Some people can use percentage to compare it. That is okay. I just find gram per mil is easy because that's what's literally given to you. So let's do this. All we gotta do is find out which one is more concentrated. Let's do green on the left. So we need to have solute, in this case salt amount over solution. Volume. Like I said, volume doesn't change just because salt is dissolved. They just become aqueous solution. They don't add the volume. So what I'm going to do is 10 gram over 50 ml. I can simplify this guy, divided by 10, then it's 1 over 5. Actually, even easier. Instead of going this way, sorry, I just changed my mind while I'm teaching. I'm actually going to multiply both by 2. I wonder people know why I am multiplying this by 2 instead of dividing. Why do you think I'm multiplying this by 2? Because 50 multiplied by 2 is 100 mil, am I right? 10 times 2, that's 20 gram. That, sorry, it's already a good decimal comparison. 20 over 100 is 0.20. That is my concentration. And you will know why I chose 100 mil. The reason is it's kind of easy match with the other one. The other one, same thing. Salt is my solute, solution on the bottom. Sorry. Because I matched to 100 mil in previous one, I don't need to change this guy. 25 over 100 is actually 0.25 in decimal. Which one is more concentrated now when we match to 100 mil? It's easy to see that the one on the right is more concentrated. So I can conclude that this beaker on the right side is more concentrated one. The beaker on the left side, on the other hand, is more diluted one. That's my conclusion of this example. I think I mentioned to you what happens if you constantly add solute more and more and more, while water does not really change, or we don't add water additionally. Then what happens is excess solute will remain at the bottom of the flask. We call it oversaturated situation. Oversaturation. Some people call it supersaturated situation. If I show you as a diagram, as you can see, unsaturated, we can still dissolve it. This is a lemonade example. Saturated situation is we are at the limit, maximum limit. If I oversaturate, like I said, supersaturated, then that's where you will see solute kind of, how can I say, solute will go down at the bottom and it will have another layer. Solute will just sink. No more dissolving is possible. This is almost repetition, so I will just let you write. Unsaturated solution is a solution where more solute can still be dissolved. Saturated solution, on the other hand, is solution in which no more solute can dissolve at a given temperature. And this given temperature, we're going to talk about why this is significant in next lesson. But at this point, at certain temperature or at a given temperature play a huge role. Temperature can change the game. Long story short, we're going to learn about solubility and temperature relationship. Every solution have a certain saturation point at a given temperature. So technically, and like I said, I'm going to elaborate a little more later. If you look at the graph on the left side, what happens if I increase the temperature as time goes? Then the amount of solubility goes up. That's a fancy way of saying for solid, if I raise up the temp, more solute can dissolve. For gas, on the other hand, it's opposite. If I lower the temperature, can you see my solubility goes up? For a gas, low temperature will increase solute that can dissolve. Why part will be explained to you in next class. And obviously, to understand the solubility and temperature relationship, we have to keep certain thing as a constant. We call it controlled variable. Now, let's think about this a little bit. Temperature is something that we change on purpose. We call it manipulated variable. It's a fancy way of saying we change on purpose. Change things on purpose. What do we observe? We call it responding variable. Fancy way of saying, what do we observe? This is so what part of it. So we change the temperature to see how much it dissolves, something like that. Control variable in this case is probably something like how much solvent do we use, a fixed volume. Those are something that you need to know. That was today's lesson, and I want you to go to lesson number 4 booklet and work on your homework.